Texas enjoys one of the best road systems in the world, with over 76,000 centerline miles on the state-maintained system. All made possible by personnel working constantly to increase knowledge of design, materials, construction, and maintenance. In pavement management, this knowledge base is dependent on input from several sources: engineering judgment, laboratory testing, field testing, test roads, computer simulation, pavement performance studies, and accelerated pavement testing. These sources provide information to develop design models which predict pavement response to loads so that the useful life of a given pavement design or rehabilitation strategy can be determined. Information about pavement material response to load is obtained from lab and field testing. However, researchers learn much more by testing with real traffic operating under actual conditions of load, climate, and subgrade. Test tracks, such as the ASHO road test, accelerate the testing process by applying truck traffic loads at relatively high speeds on closed test loops. The ASHO test, completed in the early 1960s, involved actual trucks being driven manually approximately 21 hours a day over a 2-year period. Cost, an estimated $27 million. Although researchers learn much, the fixed locality limits the number of environments and subgrades which can be evaluated. Pavement performance evaluations, such as the long-term pavement performance study currently being conducted by the Strategic Highway Research Program, SHARP, provide increased knowledge of pavement behavior to both load and environment. These studies will be of great benefit, but require years to complete, and therefore cannot provide rapid evaluation of new technologies. One of the most promising sources of information is accelerated pavement testing. This method uses vehicle simulators and has increased in use the last 20 years. The Heavy Vehicle Simulator, HVS, has been in operation in South Africa for the past 15 years. This has provided valuable insight into accelerated pavement testing while providing fast answers to pavement performance questions at a high benefit-to-cost ratio. The HVS simulates traffic by applying an overload to a single or dual-wheel carriage, which travels longitudinally along the machine. The wheel travels at approximately 8 miles per hour and can traverse laterally within a path 5 feet wide. About 1,200 18-kip equivalent single-axle load coverages, easels, can be made in an hour on a 32.8-foot-long test strip. The Accelerated Loading Facility, ALF, was designed and constructed in Australia. Like the HVS, the ALF applies load to the pavement through a single or dual overloaded wheel carriage, which travels along a linear path. The wheel travels on the pavement at about 12 miles per hour until it reaches the end of the test strip, and then is picked up and returned to the opposite end for the next coverage. The ALF can apply about 380 18-kip easels in an hour on a 40-foot-long test strip. The Federal Highway Administration has purchased an ALF machine which has been used to test pavements in Washington, D.C. at the Turner Fairbanks Research Center and in the western United States. This test was performed on an interstate highway in Montana.
In 1988, the Texas State Department of Highways and Public Transportation and the Federal Highway Administration initiated a research program at the Center for Transportation Research here at the University of Texas to develop a device for accelerated pavement testing. The device is based on a provisional patent of Dr. Frederick Hugo of the University of Stellenbosch. After the feasibility study was completed, next the department decided to develop this new testing machine and call it the Texas Mobile Load Simulator, Texas MLS. The Texas MLS will be a mobile testing device capable of accelerated simulation of real traffic loading on any selected pavement section, such as the HVS and ALF, with the additional features such as 1, closer simulation of real traffic, 2, increased application rate of axle loads, 3, flexible to suspension, axle configuration, and tires, 4, adaptable to new pavement technologies, and also 5, mobile or fixed operation.
The department acquired a 1:10 scale model of the Texas MLS through CTR to evaluate the electrical and mechanical systems to design a prototype. An examination of the model has provided a better understanding of the Texas MLS concept. The department will use the Texas MLS model in a controlled environment to determine if data collected from model test pavements can be extrapolated to full-size pavement structures. The features of the full-scale Texas MLS will provide the versatility to reproduce the effects of many different variables on the rate of deterioration of the pavement. It will be capable of utilizing existing truck suspensions, such as the forespring and the airbag. The Texas MLS will also support an assortment of truck axle configurations, such as single axles, tandem axles, and tridem axles, as well as the ability to have these axles either self-driven or trailing. It will allow the evaluation of many truck tire types, such as high-pressure tires, radials, bias ply, super singles, and new tires as they are developed. It will allow variations in loading conditions, such as legal loads, overloads, static and dynamic loads, and several types of resistance to forward motion, such as steep slopes. It will be able to vary load sequence, thereby producing varied pavement rest times. It will operate at a speed of 20 miles per hour and have the ability to brake and accelerate. The Texas MLS will be capable of applying approximately 11,000 legal single axle loads, LSAL'S, per hour, or 2 million axle loads in less than 14 days, which is far less than the 2 years it took at the ASHO road test to apply approximately 1.2 million ESLs. The mobility features of the Texas MLS allow for field testing in different climatic zones during all 4 seasons. Its mobility allows testing of pavements constructed on different soil types and geological formations, as well as seasonal changes to these variables. This mobility affords the opportunity to establish test sites on in-service flexible and rigid pavements, specially constructed test sections, short span, and model bridge structures. These unique features of the Texas MLS will provide a multitude of applications. It will be possible to apply accelerated destructive pavement testing to a vast multitude of problem areas which were not feasible to test using any existing accelerated testing facility. One of the major benefits in applying the Texas MLS for accelerated testing is the fact that the Texas MLS will not depend on the assumptions of the fourth power law to accelerate load, but will be able to apply actual load with increases in the frequency of applications. This independence from assumptions will permit the Texas MLS to evaluate such things as the validity of the fourth power law, flexible and rigid pavement design models, as well as rutting and fatigue models. In addition, the Texas MLS will be used to test existing and future paving materials, construction equipment and techniques. On short-span bridges, it will be able to evaluate the effects of repetition or volume of traffic, dynamic loads, and overload. The Texas MLS can also produce answers for maintenance and rehabilitation strategies to ensure the optimal alternative. This is especially beneficial when considering strategies using new paving materials and construction variation. The rate of application of legal single axle loads combined with the flexibility and adaptability to model new and existing suspension, axle and tire technologies make the Texas MLS a valuable tool for studying the behavior of pavements. The advantages of performing accelerated pavement testing with off-the-shelf suspension systems with actual legal loads or overloads in varied environmental and soil conditions on full scale, in-service or specially constructed pavements has led Texas to select the Texas MLS concept. The mobility of the Texas MLS will further increase its value to the department by allowing data acquisition on any roadway in the state. As data is acquired and studied, new information, knowledge, and applications will be generated. This knowledge will help pavement engineers improve design models and develop new models. These improved models will aid our quest to provide the best highway system possible.